I'm going to try. This is perhaps a little experimental talk in the sense. Originally, I wasn't actually going to do slides. I was going to do this entirely handwritten. But then the emails from the organizers made me feel guilty and like I should have slides. So I made some slides, but I also am going to work some on the tablet as we go through here to kind of slow us down and hopefully make it more beneficial to all of us as we go through here. So I'm kind of dually working on the tablet and my computer. That means actually that I can see the chat as we go through here. So if you have any questions, feel free to ask them in the chat or to mute yourself and ask. And let me try and give a little flavor of what's going on here. So, I mean, what are probabilistic methods and why are they something that we might care about? And if you've been coming to the talks this far, or if you've worked in graph theory much at all, you know that often in graph theory, we're trying to find objects that are in some sense very difficult to find. That I'm frequently presented with a graph and I'm interested in finding parameters or estimating parameters of the graph. Things like what's the largest independent set or the largest complete subgraph, or what's the smallest dominating set, or I'm interested in finding graphs with kind of bizarre properties. So graphs that contain no large cliques or large independent sets, or graphs that have kind of conflicting properties somehow. On one hand, they're locally tree-like, they have large girth, but on the other hand, they have a large chromatic number. And often, even if I'm presented with a graph and with a computer even to do this, these are kind of algorithmically difficult things to find. Like, it's NP hard to find the smallest dominating set, or the largest independent set, or the largest clique, or the chromatic number. All of these things are very difficult. And so the probabilistic method gives us a way of both estimating parameters of graphs and also a way of constructing graphs with perhaps these surprising properties. Not by constructing them explicitly, but actually by showing that they must exist because a random object has these properties. And this is a little bit difficult to wrap our heads around at first. So I would like to, as I say, explore this theme and explore these ideas during this talk. Now, one thing that I'd like to say is that if you've been attending the other talks this week, if you're going to Professor Gooden's talk tomorrow, one thing that the other talks this week have in common is that they're about different, really, areas of graph theory. And while one can study random graphs as their own as an independent object, I want to really highlight that probability in combinatorics gives a method, and this method can be employed in many, many, many areas, and including those of all the other speakers that we've seen this week. And in fact, both speakers so far have alluded to results where the proofs are probabilistic. And I'll try and highlight that as we kind of go through this. But this is the plan. Is I'd like to show you some examples of how a little bit of probability can kind of go a long ways in helping understand the structure of graphs and construct graphs with many, many interesting properties. Now, this is a talk on probability, and I don't know how much people know about probability, but the good thing is that actually, for the point of view of this talk, we won't need so much. That kind of even our bare intuitive level of probability will probably be enough to escape by for most of what we need. And I'll try and make everything self-contained in terms of what you need to know. So just a few concepts that we should be like a little bit familiar with. One is the notion of a random variable. I mean, when I do something probabilistic, what I'm going to do is I'm going to do some experiment. Maybe it's a thought experiment, but I'm thinking of doing some experiment that's going to put a probability distribution on, say, graphs or subsets of a graph or something. And often what I'm interested in is some quantity that I get from the graph itself. That's often numerical, perhaps a graph parameter. And that's what we might call a random variable. It's just a number based on an experiment. So if you want a really simple example to keep in mind, you could imagine flipping a coin, fair coin, 100 times. Well, how many heads do you get? I mean, okay, that's a random number. And it could be potentially anything between 0 and 100. But nonetheless, it's a random number that we have some understanding of. And our first base level understanding comes from what's known as the expected value of that random variable. The expected value of a random variable is just a weighted average value of this random variable. So intuitively, in this example where I flip a coin 100 times, we know that the average number of heads I should expect would be 50. Okay. This is something I can intuit, but this 50 is indeed this expected value. And a key property of expectation is what's known as linearity of expectation. That the average of the sum, the expectation of the sum, is just the sum of the expectations. Now, this is something that when we intuitively compute, oh, I flip a coin 100 times, I expect 50 heads. This is something that we're actually using entirely intuitively. That we're keeping in mind, okay, each coin has a 50-50 chance of being a heads. And what I'm doing is I'm adding up that 50-50 chance. I'm adding up that expected half of the time it should be heads over the 100 coins to get the expectation of 50. But quite critically, this linearity of expectation works when the random variables are independent, whatever that means. I don't need to think about it too hard for this right now, or entirely dependent. This works if y equals x. This works if y is 1 minus x. This works actually regardless of the relationship between x and y. And that is a really powerful fact, as we shall see. And the first step towards actually like understanding things probabilistically is just, okay, so I can compute an average value of this random variable. And that means that sometimes this random variable x is going to be bigger than average. That means for some outcomes, I'm going to be bigger than average, or at least as big as the average. And sometimes I'm going to be at most as big as the average. And this gives me a way of actually saying that an outcome of this experiment with some property exists, even without explicitly constructing it. So let's move forward and start looking at some examples of how this very, very simple idea can actually already say some very interesting things. So I want to start. I will admit that I'm doing a lot of the hits here. So if you've seen probabilistic methods and combinatorics before, you will have seen some of these results before. But I'm trying to give you both an attractive and kind of simple introduction, and showing some of the most beautiful results to give us a little bit of a flavor of what's going on. And perhaps the most famous first place you will see probabilistic methods is in the study of Ramsey numbers. So the diagonal Ramsey number R of t is the minimum n, so that any m vertex graph contains either a clique or an independent set of size t. Sometimes you hear this phrased as coloring the edges of a complete graph red and blue, but that's really the same as taking the blue edges to be your graph and the red edges not to be in your graph. All right. And Ramsey, giving this the name, proved that this actually exists. That there is, if I take a large enough n, I will always have a complete or empty subgraph as large as I like. Now, Erdős and Szekere, unfortunately, shortly after writing this paper, Ramsey passed away very young. And this result was almost lost, but it was rediscovered a few years later by Erdős and Szekere, who reproved Ramsey's theorem and actually gave an explicit bound on these numbers. In particular, Erdős and Szekere proved this kind of exponential upper bound, that R of t is less than this binomial coefficient, 2t minus 1 choose t minus 1, which if you kind of squint at it and think about how large this is, it's like 4 to the t, maybe 4 to the t over root t, but basically like 4 to the t. And you can compute out a few small values of this. For instance, it's a common thing that probably many of you have seen, that R of 3 is 6, R of 4 is 18, but it's a hard thing to compute. Even R of 5 is unknown at this point. Now, you look at this upper bound and you say, well, that's pretty big. Maybe I can do better. I mean, maybe 4 to the t that grows very quickly. If you actually try and sit down and construct graphs with no large clique and no large independent set, it's quite hard. And maybe this isn't that good of a bound. And in the 40s, Erdős proved a lower bound on this. Okay, so I've stated it in somewhat of a unfriendly way, but this is how it's often stated, that if some inequality relating it to n and t holds, then this Ramsey number is bigger than n. Now, if you go through and you compute the asymptotics of this, this gives something like R of t is at least square root of 2 to the t. And this proof, which I want to show to you in its entirety because it's beautiful and easy, was in some sense the start of the probabilistic method. Now, I should mention that, okay, so this Erdős-Szekers result is from the 30s, and this Erdős result, lower bound, is from the 40s. And yet, despite the intervening 75 odd years, the improvements to both of these are extremely mild. So the lower bound, this bound here, so this bound has been increased by a factor of 2. That's it. And this upper bound, I can divide by an arbitrarily large polynomial in T, but the essential 4 to the T-ness of it remains unchanged. Both of these after a lot of effort. So this is quite hard. All right. So let's actually kind of work through this. So I want to show that R of T is bigger than N if this wacky inequality holds. So N choose T, 2 to the minus T choose 2, plus 1 is less than 1. Obviously, this inequality is cooked up to make something work. So let's see if we can figure this out. That means I want a graph on M vertices with no clique or independent set of size T. If I find such a graph, then I've won the game. Then I've shown that this Ramsey number is bigger than M. All right. So here's what I'm going to do. I'm going to choose a graph on M vertices at random. I'm going to flip a fair coin for each edge. And if I get a head, that means an edge. And if I get a tail, that means no edge. Now, let's think about an S of size T. So somewhere in my graph, in fact, many places in my graph, I have kind of vertex sets of size T. And so what's the probability that this S is complete? That means for every possible edge that I have here, every single possible one, I would have had to do this coin flip and gotten a heads. Does that make sense? Reaction thumbs up if that makes sense. Reaction cry face emoji if I've completely lost you. Yeah, okay. I see more heads than cry faces. Actually, I only see my cry face. So perhaps I'm the only one confused right now. That would figure. All right. So the only way this could be complete is if I only got heads. And that would mean that this 1/2 chance would have had to come up T choose 2 times. And this is the same as the probability that S is independent. Again, I would have had to have tails come up this time. So now I can think, what is the expected number of complete or independent sets of size t? Okay. Well, for each individual set, the chance that it's independent is this 2 to the minus t choose 2. But actually, there are two ways that it could be complete or independent. So that's where this plus 1 is coming from. That's really multiplying by 2. That's considering these two chances. And I'm adding up over all the different t subsets. So this is like the chance for any one of them. There are n choose t of them that could potentially be complete or independent. This is the expected number. It is, by hypothesis, right? That's what this says, less than 1. Ah, it's like I cooked the books to make this inequality hold. But what did that mean? That means that the average number of these is less than 1. Well, if the average number is less than 1, there must be a real instance, a real outcome where this is less than 1. And the only way this could be less than 1 is if it's 0. So there must be some way in which this is 0. That's the probabilistic method. I've done something. I've looked at some random experiment, and I've shown that, somewhere out here in this space of graphs, there must be something small, at most this average. There must be some graph that has actually 0 complete or independent sets of size t. I haven't built it for you. I haven't shown it to you. It's a hard problem. In fact, it's an open problem to give explicit constructions of such things for arbitrary t. And yet I've shown it exists. How are we feeling? Thumbs up, cry face, sleep emoji. It's 7:30 a.m. here in Denver, so maybe I should give sleep emoji. So mostly thumbs up. I hope it's going okay. So I want to move on. All right. And in many ways, this was a really simple proof. I just literally took a random graph here, and I showed with at least positive probability it had the property I want. And I did it by just computing an average. And actually, this very, very simple idea turns out to have a ton of applications. And in order to build our intuition a little bit, I'd like to give you some more. Well, now My keyboard on my tablet seems to be having trouble, but that's okay. I don't really need it, except for now I have to scroll kind of sideways. So let me give you a few more examples of how this kind of thing worked. So yesterday, Professor Henning gave a talk on dominating sets, and he introduced us to some work on the domination number. So just as a reminder, if you weren't here, if you happen to have to not know what a dominating set is, it's like a very simple object, actually. A dominating set is a dominating set is a set of vertices so that every vertex is either in the set or at least adjacent to a member of the set. And the domination number is the smallest, the size of the smallest dominating set in the graph. And as Professor Henning told us yesterday, I mean, actually, finding the smallest dominating set is a hard business. That it's NP hard to find this number, and finding kind of the worst case when you have minimum degree 3 or minimum degree 4 or minimum degree 5, like this is already pretty serious business. And another thing that he did yesterday is he alluded to this result, which I want to show you here, that although this is very serious business and there's some difficult, hard mathematics here, there's actually an upper bound that he mentioned last time. It's almost a folklore theorem, but so far as I can tell, it's due independently to Lovász, Arnautov, and Payan. And it says that if I have a graph with some minimum degree, delta, then there's an upper bound on this domination number that looks like n log delta plus 1 over delta plus 1. So like n log delta over delta. Well, okay. And I want to prove this. Now, in order to prove this, so I have a graph. I want to find a dominating set in the graph. I don't know anything about the graph except for its minimum degree. And therefore, in some sense, I'm trying to find this without knowing much. And so, okay, one idea is I just spread a bunch of vertices around randomly and hope they hit everything. Hope they dominate everything. So I'm going to pick some probability P, and I'm just going to sprinkle in vertices. I'm going to select vertices to be in my set with probability P. This is good for dominating. It kind of spreads things all over. I understand how many vertices I picked. I picked P times N in expectation. And I mean, the problem is that this is not necessarily going to be a dominating set. In fact, more likely than not, it's not going to be a dominating set. Unless I pick P to be kind of outlandishly large. But I can figure out the probability of vertexes not dominated. Well, it depends on its degree, right? If I have a vertex, what does it mean for it not to be dominated? It means I didn't pick it to be in my set, and I didn't pick any of its neighbors. So each of these, I got a tails on. So this probability is like 1 minus P to the degree of V plus 1. Itself and all of its neighbors failed. I've got a minimum degree, delta, so I can upper bound this. Okay. So now I've got this set. I've chosen it randomly. It doesn't dominate everything. But I can make it a dominating set. I can fix everything by just taking all the undominated vertices and adding them to my dominating set. So suppose I just take all the vertices that I haven't dominated, and I'm just going to add them to this set that I initially picked. So I start with this set X that I just picked at random, and then Y is going to be everything that I missed in the first round. I'm not even going to worry about trying to do it efficiently or anything like that. I'm just going to take everything I missed and I'm going to stuff it into my set. So hopefully it makes sense that this amalgamation, X union Y, this is a dominating set. They don't have a sideways thumb on Zoom. It's a little bit of a problem, but hopefully it makes sense. And now I understand how many vertices are in this set on average, because or at least an upper bound on it, because I know the probability that a vertex is undominated is this 1 minus p to the delta plus 1. Yeah. On the next line, yes, E is going to be indeed 2.718281828 da 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 da. All right. And I now understand, okay, the expected size of this entire dominating set I picked is whatever it is, n times p plus 1 minus p to the delta plus 1. And now I can think, okay, well, this is true for any p. I should now just try and pick the best one. So I should now try and optimize over p. Now, of course, that's now a calculus problem, right? I have p is between 0 and 1. I can now try and solve this calculus problem. It's a little bit of a mess, right? I'm trying to take some derivative of 1 minus p to the delta plus 1 and try and plug it in. So there's a little trick here to get something that's a little bit cleaner. And that's exactly what I think it's Shaheen is alluding to here. That what I've done here is I've used just a little real number inequality. That 1 minus x is less than or equal to e to the minus x. This is true actually for all real numbers x. You can check it after class, right? Okay, it's a quick calculus problem to check. And this is a good approximation if x is small. It's a worse approximation as x gets bigger. But I have used this here. And the point is now that the last step of all of this is to optimize. Now I've got some bound. It depends on p. This bound holds for any p. So I should find the best p. And that's a calculus problem. I can minimize this expression using calculus. Take the derivative, all that jazz. And I find if I take p to minimize this, then I get exactly the result I promised, that this expected value of this dominating set that I chose this way is at most what I pinky swore to you it would be, n log delta plus 1 over delta plus 1. Now, this is a random dominating set, but the average size of this random dominating set is at most what I promised you here, and therefore the graph contains a dominating set of that size. And that's what I need. Now, if you were at Professor Henning's talk yesterday, he suggested that I would probably give this proof, and I did. You're welcome. But he also actually suggested that there's another way of proving this, which is just to analyze the greedy algorithm. So if you want to pick a dominating set, what you can do is you can just iteratively pick the maximum degree vertex, delete it and its neighbors, and repeat. And if you travel that and follow it through, it actually gives you the exact same bound. So one can ask then, well, okay, so that actually gives an algorithm that actually constructs a set. What's the benefit of this non-constructive version? I actually provided you this dominating set. I've just shown it exists somehow. But one thing that I want to highlight is that in many ways, it's the ideas and this probabilistic method that are more important than the result. Once you have the idea, you can take it and run with it. For instance, I can use this exact same method to get bounds on, for instance, lots of different dominating things. So when I wrote these slides, I thought perhaps Professor Henning would mention total domination, and he mentioned that he wouldn't mention it. But total domination, for instance, is that I want every vertex to have a neighbor in X. As opposed to either to be in X or to have a neighbor in X. In other words, I want to make sure that the vertices in X have other neighbors in X other than themselves. Okay, well, actually the same proof, exact same proof works. I just have now that the probability that I'm undominated well, what would it mean? I have a vertex. I no longer consider me to dominate myself. So what does it mean that I'm not dominated? It just means that I got tails on all my neighbors. So I get something like 1 minus p to the delta instead of delta plus 1. That's actually the only difference between these two. Okay, so I get a slightly different result because I will pick a slightly different p, but the idea is exactly the same. If you're interested in finding sets that dominate every vertex up to some distance, again, you can turn this into a thing. All you need to know is kind of a bound on how many vertices lie at some distance, so you can estimate the probability that I'm undominated. And the stronger kind of my neighborhoods expand locally, the stronger bound I get. But I can use the exact same idea, and I can use it to prove actually many theorems. Another thing that Professor Henning alluded to yesterday that I will mention is independent domination. So what if you want an independent set that also dominates all vertices? That is, in some sense, a maximal independent set. And this is somehow harder business because if you try the same thing, you just pick a bunch of vertices randomly, you're not actually that likely to get an independent set. So you would have to like modify this initial set X to get rid of neighbors vertices that were neighbors to each other. And you kind of either end up not taking enough initially, or you end up deleting too much and you have to kind of play with it. And just to give you a sense that things get complicated, but it can actually work, is actually you can make this kind of method work, but you need to pick random vertices in many steps, do what's known as a Reutel nibble. That's a much more technical procedure than what I just showed you. But actually, if you have a graph that is both regular and girth at least 5, then you essentially, for independent domination, recover the result I told you about. That the independence domination number of a deregular graph of girth 5 is like n log d over d plus a constant. And very interestingly here, both this girth condition that you have girth at least 5, this is necessary because if you take something like a complete bipartite graph, and it's very easy to dominate, but if you want an independent dominating set, you need to take half the vertices. And actually, the regularity is required as well, that you can construct graphs that aren't regular, and you don't get anything like n log delta over delta with the minimum degree. So hiding under the surface here, there's a lot of other results. But nonetheless, this really simple mantra can be used to do quite a bit. And we'll see maybe another example or two in the problem session, just to kind of see how we can take an idea, and once we have the right idea, we can kind of run with it. Let me give you another example along these lines and look at the max cut problem. So the goal is, I have a graph, and I want to partition my graph into 2 parts so that as many edges go across the cut as possible. And finding this, or even actually approximating it closely enough, is NP hard. So it's NP hard to approximate this within a large enough factor. Nonetheless, there is at least something you can do. So every graph turns out to emit a bipartition into 2 sets, so that at least half of the edges of the graph are across the cut. And let me prove this really quick. All right, so I'm going to randomly place vertices in X or Y, each with probability 1/2. Half and independently. That says independently, I promise. All right. So I just flip a coin. If it's heads, I put a vertex in X. If it's tails, I put it in Y. And now I think, okay, if I fix an edge, the probability that E crosses the cut right. Well, it's 1/2, because wherever one end goes in, the other end has to end up with the other set, which happens with probability 1/2. It could be in either side. So actually, the probability that this edge crosses the cut is 1/2, and therefore the expected number of edges across the cut is 1/2 of all the edges. This is the average number of edges across the cut. Some choice beats the average. Ergo, I have the bipartition I want. The same idea as these other methods, that I compute some average and I go with it and I get a nice result. All right. Now there's another proof that you may have seen of this result, which is non-probabilistic. And also extremely beautiful, and in some sense it gives you a little bit more. That what you can do is you can start with an arbitrary bipartition, and now you just do the following algorithmic thing. If you have a vertex on one side that has more neighbors in its own set than in the other, you switch it to the other side. And you just do this. Every time you have a vertex that has more edges in its part than in the other part, you switch it over to the other side. This process eventually stops because every time you do this, the number of edges across the cuts increases, and it can't increase forever. And once you do this, you'll actually have a bipartition where every vertex has at least half of its neighbors in the other side. Well, that proved the result in a very nice, clean way. So what's the point somehow of this random proof? And the point is, once you have a good idea, you can run with it. This random proof generalizes in many, many nice ways for free. For instance, well, what if I partition into 3 parts instead of 2? I mean, I can modify the proof that I just give you. I just put vertices in X, Y, or Z, with each with probability 1/3. Then the probability in edges between 2 of these sets is now 2/3. So there's a tripartition with 2/3 of the edges across the cut. You want to do it with 4 sets, 5 sets? No problem. Or suppose you really care about the sizes of these sets. The original proof I gave you, not the original proof, the non-probabilistic proof I gave you, I don't actually really control how big the sets are at the end. I'm flipping things back and forth, and who knows how large exactly the sets are at the end. Even in the probabilistic proof, the size of the sets is a random variable. But you could do something like the following, that you just randomly arrange the vertices, you randomly partition the vertices, take the first half, call that X, take the second half, call that Y, compute the probability that an edge crosses the cut. It's still actually at least 1/2. And therefore you can partition into 2 sets of the same size. I can tell that at one point here I didn't want to deal with floor and ceilings, and then I changed this. So I don't need this to be even. That's a little bit of an embarrassment on my part. Does it make some sense? So actually I can control the size of the sets. Well, what if I want different size sets? I can actually take my graph and split it into an alpha size portion and a 1 minus alpha size portion, where, okay, I can compute how many edges I expect across the cut. This 2 alpha times 1 minus alpha is the expectation there. One can kind of crank it out. And I get all these results. Actually, because I've been trying to mention something related to all the speakers of this workshop, let me mention something that I found really quickly yesterday related to tomorrow's speaker. This doesn't have to do with directed graphs. It actually has to do with this problem. And this is in kind of a trick used in a recent paper of Guden Yao on these kind of max cut problems. And it's just a very nice observation. I don't even know whether it's originally theirs, but it's a really beautiful observation that I found when I was just looking at the Wikipedia page for max cut to make sure I wasn't saying nonsense yesterday. And they make the following observation. Suppose I know that somewhere in my graph, I have an induced bipartite subgraph. Actually, what they do is a little bit harder than this, a little bit more complicated than this. So suppose I have an induced bipartite subgraph. And then I can take part of this induced bipartite subgraph. I'm just going to assign it to X. And I'm going to take the other part of it, and I'm going to assign it to Y. And all the other vertices, every other vertex has some edges maybe to X and to Y. And I'm going to assign this randomly. So I fix a graph. I make sure I cook the books so that all of those edges cross the bipartition. Every other edge, every other vertex, I assign randomly. And now what I have done is I've cooked the books so that I've guaranteed that all these edges cross the cut. And every other edge has a 50-50 chance of crossing the cut. So that means that actually the expectation has improved. So I fix X and Y to guarantee that the induced bipartite graph crosses the cut. And now I guarantee more edges. And I can always find at least some induced bipartite graph. I mean, maybe it's a single edge. Really, I can do better than that. But I can improve these kind of ideas. I can take this idea, I can run with it, and I can get a stronger result. All right. So what's the problem with this? Now, one problem with this is that as much fun as we've been having, I'm still limited to dealing with averages. And that means that I can't really recover any theorem like this other one I mentioned, that I gave this algorithm for finding this bipartition. And this algorithm actually guaranteed that every single vertex, after it was done, sent at least half of its edges to the other side. If I do things randomly, like on average, half of vertices and neighbors are going to be on the other side. Some are going to be more than that, but some are going to be less. I'm not actually attaining this by partition. And this is really showing me that there's a limit to working with averages. So I've got a half hour left. I want to take a step beyond what we've been doing so far, which has all depended just on the expectation, and talk a little bit about how one moves beyond this, which is really through the use of what are known as concentration inequalities. And this gets like a little bit more technical, and therefore is a little bit harder for an hour and a half talk. It's like more appropriate for a course. But nonetheless, I want to give you at least a sense of how one moves beyond just computing an average and concluding magic, which is what I feel like a lot of this talk so far has been. All right. So far, we've just been talking about random variables in terms of their expectation, their average value. And it's easy to say that if I have one random variable, it's sometimes bigger than its average. But what if I have two random variables that I care about? I care about the degree of both this vertex and that vertex. Well, then it can be hard to say that they're both large at the same time. I know that one is sometimes large. I know that the other is sometimes large. But how do I know that these both happen at the same time? What I would like to know is that often I'm at least reasonably close to this average. And then I can ask for different random variables to be close to the average at the same time. And the way I can do this is through what's known as concentration inequalities. What's a concentration inequality? Well, it's just an inequality that helps me understand how likely it is that my random variable x differs by its expectation by much, by more than lambda. So this is a weighty business. There's a lot going on here. But the simplest thing kind of this type is what's known as Markov's inequality. In some sense, that's what we've been using so far. Markov's inequality says that if you have something that's non-negative, then it can't be too much bigger than its expectation too often. If it was too much bigger than its expectation too often, well, then the expectation would be bigger. It's a very simple thing, but it only controls things in one direction. It's one-sided. It's also like not that strong of a result. It doesn't actually say so much. So we'd like to move beyond it somehow. Now, the most famous thing that you may have seen before, if you've ever taken a probability class, what you've probably seen is Chebyshev's inequality. Chebyshev's inequality is really truly what I want. It's a bound that differs exactly how far my random variable is from its expectation. And it measures it in terms of what's known as the standard deviation, which is the square root of the variance. And the variance, okay, I've written it one way here. There's an alternate way of writing this, which is the expectation of how far x differs from its expectation squared. So these two quantities are the same. Again, if you've ever encountered a probability before, you've encountered the variance at some point, I'm sure. It's just a measure of how far x is from its expectation. This form, other form I wrote it in, is just often more convenient to compute it in. And it says that the probability that I differ from my expectation by more than k standard deviations decays like 1 over k squared. And so it's a two-sided bound, and very often I can compute this variance, but it's still not that strong of a bound. Now, if you've done a little bit of probability, you might know that there's more that I can do here. And at least intuitively, one of the things you may recall is a very important result in this in probability is the central limit theorem. Now, the central limit theorem says that if I have a random variable that is actually the sum of a whole bunch of random variables, well, that's familiar to a bunch of the problems we were actually working on, that I was taking sums of a bunch of things at least. So if I have a bunch of random variables that are IID, that means independent and identically distributed, so I have some expectation and some variance, then actually if I take this sum and I kind of normalize it so that it's mean 0 and variance 1, that's what all of this is doing, mean 0, variance 1, then this converges in distribution to a standard normal random variable. Standard normal, that's the bell curve. So I actually understand very well, in some sense, this sum of independent random variables, at least in the limit. Now, applying the central limit theorem directly in combinatorics is a little bit tricky because the rate of I have an n variable graph, n is finite, and I'm usually interested in actually understanding finite, although perhaps n large graphs, and so this, as a result in and of itself, isn't that useful, but there are kind of finitary versions of it. Perhaps the most useful is this so-called Chernoff bound. There are tons and tons of variants of this that change various things, but here's a very simple version. So suppose I have a random variable x. It's the sum of a bunch of random variables. My dog wants out of my office. He let himself into my office, so it's a little bit rude of him. Okay, sorry. I have a random variable that is the sum of a bunch of other random variables, where these are independent, and they're either 0 or 1. I don't actually need them to have the same distribution. Then what this does is it bounds how far I am from my expectation by something that decays like, well, e to the minus lambda squared over 2 with the expectation and some other term that is unfortunate but is there. And it's a lot to kind of sink in a very, very brief time. But what this is saying, essentially, is that if I pick this lambda, much bigger than the square root of the expectation, then this probability goes down. And it goes down fast. It decreases exponentially. And it's broadly applicable. That often I can think about various parameters that I'm interested in studying as sums of independent random variables. And if they're not 0 or 1, there are other variants. There's a lot you can do with this broad idea. This is just a form that is relatively succinct to state and relatively useful to actually use in practice. I will mention that this is really just a taste of a subject that could go on and on and on and on and on and on for weeks. There are lots and lots of other methods that are used to get concentration. But this at least gives me a start. And in my time left, I'd like to give you just a taste of using some of this. And to do that, let me look at another object that people like to study. And these are the so-called Erdős-Rényi random graphs. It's interesting. It's a little bit of a misnomer in that this wasn't the original model that Erdős and Rényi studied, but it's simpler and it's easy and it's got the name. So this is a random graph model where I generate a graph. It's a labeled graph on m vertices by flipping an edge, flipping a coin for each edge, and taking the edge with probability p. So if p equals 1/2, then actually what I have is a uniform distribution on graphs. Every labeled graph has the exact same probability of appearing, which is 2 to the minus n choose 2. This is actually exactly the model that we looked at earlier when we looked at the Ramsey number. And people often vary this p to get graphs that have different properties, or at least likely to have different properties. So one might take some p depending on n. For instance, like p is 1 over n, or 1 over square root of n. And the smaller this p is, the sparser graph I will get out on average. So I am going to expect the p fraction of my edges. Again, the sparser p, the smaller p is, the sparser graphs I get on average. Now this is a random graph. Presumably I could get any graph in the world from this, but the likely outcomes are going to depend on this p I pick. And the theory of these graphs, it's a beautiful theory that people study both for applications to other areas. These provide lots and lots of nice examples, but there's also a lot of beautiful structure within these problems. For instance, there are a lot of phase transitions. As I change p, I will see different behavior. So for instance, if I take p like a little bit smaller than log n over n, and I take a random graph from this distribution, then almost certainly it will be disconnected. If I take p just a little bit bigger than log n over n, then almost certainly it will be connected. And there's all sorts of fascinating stuff here. This is a topic in and of itself. But let's see a little bit how these inequalities can help me understand things. So let's briefly just work through a few properties here. So question 1, so how many edges does a random graph in GMP have? I mean, it's a random variable, of course. I generate a random graph using this. I could have anything between 0 and n choose 2 edges. But the expected number of edges is, well, there are n choose 2 possible edges, and I expect a p fraction of them. Okay, that's easy enough. But of course, this just means that sometimes I have more edges than this, sometimes I have less edges than this. Like, how close should this actually be? And the probability that this number of edges differs from its expectation by more than lambda is shrinks like whatever I wrote before, twice this expectation plus lambda over 3. Okay. And so if I want to make this small, if I pick this lambda to be like the square root of this expectation, so if I pick this lambda to be like the square root of this expectation, then this will be like a constant. This lambda squared and this expectation are in some sense going to cancel each other out. This is like a constant. So really what I would like to do is make it go to 0. And I can do this by just tacking on some function that goes to infinity arbitrarily slowly. If I do this, then this ensures that this probability that the number of edges minus the expectation is bigger than lambda goes to 0. That is, with probability tending to 1, so let's write it here, with probability going to 1, the number of edges is between this expectation plus this square root times omega, and it's bigger than this minus times omega. All this is to say that if I'm in, say, a regime where p is like a half, well, when p is like a half, then I'm expecting like n squared over 4 edges. And I'm differing from that by something that's basically linear. It would be extremely unlikely to get a graph that is much more than some n edges away, or n log n edges away from n squared over 4. Even though any graph is possible, in fact, any graph is equally likely, almost every graph has close to n squared over 4 edges. And this works throughout. So I understand this property, even though this is a random object, I understand this property very well, thanks to this concentration inequality. And there are other things I could do. Okay, so I could think about other properties of this random graph, like the degree. Okay, so I pick a vertex V. It has m-1 potential neighbors. I'm flipping an independent coin for each of them. The expected value of this degree is just p times m-1. N is big, so for convenience, let's just think of this as being basically p times n. That's going to be my degree. And the probability that the degree of V differs from this expectation by more than lambda would like this E, the minus lambda squared, again over twice this expectation minus lambda or plus lambda over 3. Okay, so this is all well and good. But of course, there are many, many vertices in the graph. So perhaps I'd like to say something about not just a given vertex, but about all vertices simultaneously. So what's the probability that there exists some vertex V such that the degree of V differs from its expectation by more than lambda? Well, okay. This isn't most. Well, for any given vertex, I get this e to the minus lambda squared over twice the expectation plus lambda over 3. And there are n different vertices that have a shot at having this kind of bad thing happen. So if I want to control all vertices at once, now I have to pick a good lambda to make this small. And what this extra factor of n is making me do is it's making me add an extra factor of kind of a log n here. And if I do that, and I add a large enough constant, when I work it all out, this e to the minus log n will beat this n. And this probability will go to 0. In other words, almost, so with probability tending to 1, all vertices will have a degree close to their expectation. How close? This lambda. Now, getting like really comfortable with these expectations requires some work. And there are many other things that I could follow with the same kind of thing. So for instance, I'm not actually going to work these out because we're running out of time for this particular session, and I've got some other things planned, but I wanted to make sure I wasn't going to run out of things to talk about. One thing you would think about are for instance, neighborhoods, common neighborhoods of vertices. I can work that out. That gives me right away a bound of 4 cycles of my graph. And the computations look very similar. You could think about triangles. The triangles are kind of tricky because they're not independent, right? If I happen to already know that this edge exists or this triangle exists, then this triangle is more likely. So if this exists, then some other triangle is more likely. And that actually means that these kind of Chernoff bounds don't really work directly. And I need to use, for instance, the variance. But I can still understand the expected count and how far I am from that expectation. I also mentioned that this is, in terms of random graphs, this is just the tip of the iceberg. People study all kinds of random graph models. Random regular graphs, where the edges aren't independent. Random graphs where the degrees have some given distribution. And there are many more. I was thinking about this for this talk the other day, and I'll mention that there's kind of an easy way of generating these semi-transitive graphs. So you can generate a random semi-transitive graph that Professor Kitiev was talking about the other day. And I don't know whether the random model that I kind of came up with during his talk is as interesting in terms of answering any questions, but you can really think about these easily. However, let me kind of tie things up here because we're at the end of our time. And what I really want to say is these simple ideas underlying probabilistic methods have ties to really all areas of modern combinatorics. Studying objects. So in Professor Kitiev's talk, he mentioned this construction of Erdős of graphs with high girth and high chromatic number. This is probabilistic. Professor Henning yesterday mentioned this bound that we proved, and it probabilistic methods provide lots of bounds on this. Tomorrow there will be a talk on directed graphs and tournaments, and the probabilistic method plays a large role in that kind of study. Last year, Professor Dunkelman talked about distances in graphs. I don't know whether he's still here, but again, random graphs provide good examples of expander graphs that have kind of a small world phenomenon and provide examples in this area. There was a talk last year from the same school on spectral graph theory, and eigenvalues related to the graphs have strong relations with the randomness of a graph. And in fact, they kind of provide a certificate that my graph looks random. This is one of my favorite topics. And this is just like the tip of a huge iceberg. But I hope you've seen that by taking kind of simple ideas here, you can really run with them. And even in cases where probability per se isn't necessarily that useful, I find that the thinking in somewhat of a probabilistic sense or an average case sense is useful in all sorts of problems in combinatorics. And I think now is a good time to take our break. If there are questions, please feel free to ask. And we'll come back and we can work on a few problems and we can see the method in a few more instances. And I think I will stop here. So thank you all very much.